The next category of data we discuss has the form of graphs or networks, the most obvious example being social networks. Now, speaking of social networks, Tim Lipzik created a social network from the Lord of the Rings trilogy. This graph represents the characters' allegiances, that is, who is faithful to whom in the books. So the nodes are characters and other entities like cities, and the edges connecting pairs of nodes represent allegiances. So after this video, you'll be able to identify graph data in practical problems and describe path, neighborhood, and connectivity operations on graphs. Now, this specialization includes a separate course in graph analytics that provides a much more detailed treatment on the subject. Now, what distinguishes a graph from other data models is that it bears two kinds of information. One, properties and attributes of entities and relationships, and two, the connectivity structure that constitutes the network itself. One way to look at this data is shown in the figure, borrowed from the Apache Spark system. In this representation, the graph on the left is represented by two tables on the right. The vertex or node table gives IDs to nodes and lists their properties. The edge table has two parts. The colored part represents the properties of the edge, whereas the white part contains just the direction of the arrows in the network. Thus, since there is a directed edge going from node 3 to node 7, there is a tuple 3, 7 in that part of the edge table. Now, this form of the graph model is called the property graph model, which we'll see many times in this course and in the specialization. Now, representing connectivity information gives graph data a new kind of computing ability that's different from other data models we have seen so far. Even without looking at the properties of the nodes and edges, one can get very interesting information just by analyzing or querying this connectivity structure. Consider a social network with three types of nodes: user, city, and restaurant, and three types of edges: friend, likes, and lives in. The leftmost node, AG, represents me, and I'm interested in finding a good Italian restaurant in New York that my friends or their friends who also live in New York like. I shall possibly choose IT3 because it has the highest number of like edges coming into it from people who have a lives-in edge to New York, and at the same time can be reached by following the friend edges going out from me. Now, this shows a very important class of operations on graph data, namely traversal, that involves edge following based on some set of conditions. A number of path operations required some sort of optimization. The simplest among these is the well-known shortest path query, which is applied to road networks to find the best route from a source location to a target location. The second class of optimization operations is required to find an optimal path that must include some user-specified nodes, but the operation has to determine the order in which the nodes must be visited. The classical application is a trip planner, where the user specifies the cities she wishes to visit, and the operation will optimize a criterion like the total distance covered. The third category is a case where the system must find the best possible path in the network given two or more optimization criteria which cannot be satisfied simultaneously. For example, if I want to travel from my house to the airport using the shortest distance but also minimizing the amount of highway travel, the algorithm must find a best compromise. This is called a Pareto optimality problem on graphs. The neighborhood of a node n in a graph is a set of edges directly connected to it. A k-neighborhood of n is a collection of edges between nodes that are at most k steps away from n. So going back to our mini social network graph, Bob, Joe, and Sarah are the first neighbors of AG, while Max, Tim, and Pam belong to the second neighborhood and not the first neighborhood of AG. Finally, Jen is a third-level neighbor. An important class of analysis to perform with neighborhoods is community finding. A community in a social network can be a very close group of friends. So the graph shown in this figure has 4 communities. One can see in the figure that each community has a higher density of edges within the community and a lower density across two different communities. Finding densely connected parts of a graph helps identify neighborhoods that can be recognized as communities. A more complex class of operations include finding the best possible clusters, which is another name for communities, in a graph, so that any other grouping of nodes into communities will be less effective. Now, as graphs become bigger and denser, these methods become harder to compute. Thus, neighborhood-based optimization operations present significant scalability challenges. If we inspect the neighborhood of every node in a graph, sometimes we will find neighborhoods that are different from all others. These neighborhoods are called anomalous. Consider the following 4 graphs around the central red node. The first graph is odd because it's almost perfectly star-shaped. That is, the nodes that the red node is connected to are almost unconnected amongst themselves. That's really odd because it doesn't happen in reality much. So it's an anomalous node. The second figure shows a neighborhood to which a significantly large number of neighbors are connected amongst themselves. This makes the graph very cliquish, where a clique refers to a neighborhood where each node is connected to all other nodes in the neighborhood. The third figure shows a neighborhood where some edges have an unusually heavy weight compared to the others. The fourth figure shows a special case of the third, where one edge is predominantly high weight compared to all the other edges. Connectedness is a fundamental property of a graph. In a connected graph, each node is reachable from every other node through some path. If a graph is not connected, but there are subgraphs of it which are connected, then these subgraphs are called connected components of the original graph. In the figure on the right, there are 4 connected components. A search query like finding optimal paths should be performed only within each component and not across them. For large graphs, there are several new parallelized techniques for the detection of connected components. We will discuss a MapReduce-based technique for connected components in a later course.